We're continuing on here, chapter 14 here. So last time we talked about carboxylic acids. We also talked about esters. Carboxylic acid again has the functional group of carbon oxygen double bond into the OH group there. The ester, which is really sort of based off of the carboxylic acid, has also the carbon oxygen double bond, that carbonyl bond, the oxygen. But again, here it's not attached to the H, it is usually to another carbon there at the end of it, would be the functional group there for an ester. Remember that this carbonyl group is a polar group, positive and negative. That means the carboxylic acid has actually two polar groups, also allows it to, and also has a very high boiling point because of that. The ester here are positive and are negative. We talked about naming these guys. The carboxylic acid gets the oic acid ending at the end of it. Because of the functional group there and the hydrogen at the end, we do not again need to number the carbon oxygen double bond. But as we talked about in terms of numbering for other groups that may be attached, that should always be carbon number 1. And again, it will always be at the end of the molecule, either one side or the other, because of that hydrogen at the end. The ester, on the other hand, will never find the carbon oxygen double bond really at the end, because it needs a carbon on one side or the other. These guys get the group name, and then it gets the O8 at the end. And it's really based on sort of what it is made up of. We talked about how we form carboxylic acids. Again, a carboxylic acid is really formed from the oxidation of an aldehyde, which originally comes from a primary alcohol. When you oxidize an aldehyde, we insert basically the oxygen there, and that makes our carboxylic acid group. While esters are actually made up of the reaction between a carboxylic acid and an alcohol, basically. Something like that. So let's make a very simple one. And alcohol. And remember that if you kind of line up the hydrogens, what we're going to do is basically just kind of take out the water part there and basically squish everybody back together. Obviously taking out the water. And that is what is referred to as an esterification reaction. And so the naming part of this, as we talked about, you always want to remember that you want to look for the ester here between the carbon and the oxygen single bond, and heading towards the single bond is going to be our alcohol portion. And that really is where the group part of the name would come from. So for example, the group there would be a methyl group. Going the other way is the carboxylic acid part. Again, kind of going through the double bond that way is our carboxylic acid portion, which is really the main part of the name. And that we would just count up some carbons. So 1 and 2 on that, which is based off of ethane. You drop the E and put the O8 on it. And this is methyl ethanoate would be the name here. Get out of the way there, sorry. Methyl ethanoate would be our name. And again, the main part of it is based on that carboxylic acid. Obviously here, if we had this guy here, which is 2 carbons, which is based off of ethane, and we drop the last part there and put ethanoic acid as the name. Any questions on any of that stuff there? Okay. All right, so we got a couple of things to finish up talking about in terms of carboxylic acids. Then we'll get into the final 2 organic groups, I think, that we're going to talk about. So let's talk a little bit about the hydrolysis of esters. So hydrolysis usually means water. So water is involved. And ethyl acetate, as we see here, is a solvent used in fingernail polish, plastics, and so forth. But really, a hydrolysis reaction basically means we're going to add water back in. If you think about it, to make the ester, we took water out. So it's kind of like the reverse process here if we add the water back in. Now, there's two types of situations that will occur with esters. There's the acid hydrolysis, in which an acid is involved with some heat as sort of a catalyst. And if we look at what we got going on down there, I'll just draw it up a little bit higher here. And we add some water here. And again, H plus is the acid catalyst. Remember, a catalyst is there to speed up the reaction. And again, heat as well. So what will happen in the sort of acid part is it's going to break apart exactly where we put it together. So what's going to happen is this water is going to cause this ester basically to break back apart. So what that means is you really can just draw the two parts separate from each other. So I'm just going to draw it underneath. I'm going to draw the one part here, which I know because I'm going towards the double bond, that's my carboxylic acid part. I'm going to draw the other guy that's parted out there. And I know that this going towards the single bond is my alcohol part. And pretty much what I'm just going to do is rebuild both of those at this point. Thank you. So to get my guy on the left to the carboxylic acid, it needs the OH, which is right here. So this OH will then come and rebuild my carboxylic acid. And that's going to leave me an H that's left over, which is good because that H is needed to rebuild my alcohol by putting the H there. So the acid hydrolysis is essentially the reverse reaction of the esterification reaction, where you put those two together to make an ester. Water basically will split it back apart right where you put it together. And again, you will get back, in this particular case, you will actually get back both parts that you started with, the carboxylic acid and the alcohol from which it was made. Any questions on that there? So again, you can think of this as pretty much the exact reverse of the esterification reaction. So in an acid situation and the acid hydrolysis, you definitely get back both of your starting guys, the carboxylic acid and the alcohol. Any questions on that there? Okay. Now, the base hydrolysis is similar, but because we are using a base and not really water is sort of like an acid, we actually do not get back both parts of our ester. We don't get back the carboxylic acid. We do get back the alcohol part, but not the carboxylic acid. So in this sort of replaying here, we will get really part of the guy back. What we will make is a carboxylic acid sort of salt there at the end of it. So we will see this ester here. If we start with it again, we're going to take this guy here. I'll draw it up here so we take a better look at it maybe. And in this case, though, we are going to add sodium hydroxide, which is really sodium and OH here is what we're sort of have going on. And we're going to have some heat. So once again, in this case, this is definitely a base. So this is how we know it's a base. And what's going to happen is really the same sort of situation. It is again going to break this guy apart right where we would expect it to happen. And again, we could actually draw the parts like we did before. So that's our carboxylic acid part that has the double bond. We would then obviously have our alcohol part there that has the single bonded oxygen. Now, as I mentioned before, what's going to happen is we're really only going to be able to rebuild the alcohol part of it. So what's going to happen is the H over here is going to sort of find its way down to here, and that will rebuild our alcohol. Make it a different color. Now, in this particular case, not exactly that H, by the way, but we'll call it that H is going that way. What happens now in this case is we do not have enough to rebuild the carboxylic acid. But if you want to think about it, we still have an O, which gets us close to what we need. And that O is going to end up being a negative charge because we don't really have the extra H there to put on there. So in this case, what we make is a salt. So that's where the sodium comes into play. And it creates this guy right here. So this is a salt of the carboxylic acid is made when you do a base one, but we do get the alcohol back. So the difference between the acidic hydrolysis and the basic hydrolysis is the acidic hydrolysis will get you back everybody just like you started, both the completed carboxylic acid and the alcohol. In the base one, you just get the alcohol back and you make this salt. This salt that's actually made here is sometimes referred to as a saponification reaction. It is basically how you make soap. It's basically how we make soap here. A really long molecule of this guy is pretty much what soap would be. So for example, and they probably have one or not, maybe. Let's see. That will go here. So if you take a really long one and you do a base hydrolysis there of a carboxylic acid, you'll end up with one that has a really long carbon and hydrogen chain. And at the end, you will produce this carboxylic acid salt. And this is basically soap. And soap, because of this reaction, actually has two different parts. It has a part that is non-polar, which would be this part. Sometimes referred to as the non-polar tail of soap. And it has the front part, which is a polar part. Sometimes referred to as the polar head of soap. And that's really good for soap because most dirt is non-polar, which means the kind of non-polar side of soap is attracted to it. And what it does is my bad squiggles, which is all my carbons and hydrogens here. The soap molecules basically surround the dirt with the non-polar side of it. And what that does is it creates what is sometimes referred to as a micelle, which is really the trapping of dirt in a bunch of soap molecules. And what it has on the outside of each of these sort of soap molecules is this carboxylic acid part, or the salt of a carboxylic acid. And that part is polar. So we have this kind of polar part that's on the outside. We got all the dirt kind of trapped on the inside with the non-polar part. Like dissolves like, so non-polar things mix, right? And usually when we use soap, we then end up using water. Yeah. And water is polar, which means water is attracted to all the polar side of soap. So what you do is when you soap up, right, you basically trap all the dirt inside soap. It aligns all the polar part of the soap molecules on the outside. So when you wash it with water, the water and the polar part of soap will mix, and out with the wash water goes all the dirt. So you are clean. It's good to know how soap works, I suppose. Yes. So that is the idea of what happens when you do it that way and you use soap. So it really is, soap is really made through this type of reaction where you can take something like an ester or something like this or carboxylic acid and do a base hydrolysis of it, and you'll produce perhaps a soap molecule. This one probably wouldn't be a great soap because it's not a very long carbon chain. Usually they're extremely long sort of carbons and hydrogen chain on the back end of it, that non-polar part. But that's essentially the reaction that makes soap. Any question on that there? All right, let's see here. So we'll do, this is We'll take a look at it here. This is methyl acetate, which is the common name. This is more so known as methyl ethanoate. So we're going to take methyl ethanoate, and we're going to do our water and our acid hydrolysis. So the important part here is the acid part of it. So we know that in the acid part, what's going to happen is we're going to get back both parts of it completed. So once again, we're going to break it right there where we put it together. We're going to draw both parts that are left over. And really at this point, because we have water and we know it's an acid, we get everybody back. So at this point, we just need to rebuild the carboxylic acid, which means this guy needs an OH, which really comes from here. And we need a hydrogen on this guy on the right to get us back to the alcohol. So that would be what we would end up with there. Any questions on that one there? Now, the bottom one is KOH. That is a strong base. So that's going to do the base hydrolysis that we just talked about. Again, you could approach it the same way. We can take our ester. We're going to add KOH in this case. So once again, we know it's a base. We don't have water or an acid. So what we should know off the bat is we're actually only going to get back the alcohol value. So that's the only part that we're going to get back that's going to be completed. So we once again could draw the parts. And for sure, we know we're going to get the sort of alcohol back. So you could take the H and put it here. And if you want to just kind of keep track of everything, you can get rid of the H there. And now I have an O and a K. So the O should be connected here because that makes it look like a carboxylic acid. But that will also end up with a negative charge, and the K will be a positive charge. So that will give us the salt that's being made, which if you just want to kind of keep track and cross those guys off, and now we used all the letters in the alphabet there to rebuild it. Any questions on that there? So acid, as we see, we get back both things. Base only get one thing back, and we get almost the other carboxylic acid back, but we will always have basically a salt, which means we'll always end up with, in this reaction with the base, the carboxylic acid will always end up like that, basically, with some type of spectator ion, sodium, a potassium, something like that at the end. And you'll always end up with the completed alcohol for the base one. And for the acid one, you will always end up with the completed carboxylic acid and the completed alcohol. So that's how you'll always end up in both of those situations. Any questions on that there? Yeah. All right, so now to our final two sort of organic groups. The next group that we're going to talk about are amines. Amines are actually nitrogen-containing groups. They look something like this. This is the functional group. Amines are pretty much what are sometimes referred to as derivatives of ammonia. So amines are basically derivatives of ammonia. Ammonia, which is a weak base, which also means amines can really behave like bases, as we will see as well. But they're really sort of functions like ammonia and derivatives of it. Here we do have groups that are actually attached to the nitrogen. And that's a little bit different than what we have sometimes attached to a carbon. So this is an amine here. We have our nitrogen. This is what is referred to as a tertiary amine. So you could actually classify amines, as we will see, just like alcohols and carbons. And that is, you would look at the nitrogen, and it is attached to 1, 2, and 3 carbons. So it's a tertiary amine. This is also amine here, but it is actually a secondary amine, as it is attached to 1 and 2 carbons there. And this amine is a primary amine, as it is attached to 1 carbon right there. would be a primary amine. So much like, again, the alcohols and the carbons, amines are oftentimes classified by really the number of carbons that are attached directly to the nitrogen, as the nitrogen is part of the functional group. As you can see, every time you sort of add an extra carbon group, you lose a hydrogen off of the nitrogen. So this guy has basically one carbon. It's got two hydrogens. This guy has two carbons attached, has only one hydrogen. And this guy at the end here has no hydrogens because it has three carbons basically attached. So the hydrogens sort of decrease every time you add in a carbon-containing group to the nitrogen. These lone pairs basically still remain, though, on the nitrogen, the dots and stuff like that. So as I just did there and jumped gun, it is a primary, secondary, and tertiary amine. And again, the easiest way, I think, to do it is to count how many carbons are attached. As I mentioned, sometimes people will count hydrogens rather than carbons, but I think carbon's just easier. So here's, again, our primary, our secondary, and our tertiary amine, meaning 1, 2, and 3 carbon groups are attached directly to the nitrogen in each of those cases. So there's ammonia. This is methylamine, dimethylamine, and trimethylamine. One of the ways we will name amines is probably we'll roll with this, which is much nicer than the IUPAC way of naming. If we look at a common way of naming amines, we basically look at the nitrogen and see what groups are attached. So that is a methyl group, and that is where the name comes from. It's methyl, and then it's an amine, so that's not too bad. This guy has two methyl groups attached, so that is dimethylamine. And this one has 3 methyl groups attached, giving us trimethylamine. So we'll go with this way of naming. This is not really the IUPAC way of naming, but we'll go with this sort of way of naming, which seems much easier in these cases. So to name these guys, basically we take the carbon groups that are attached. We list the groups that are bonded to the nitrogen in alphabetical order. And then we simply put an amine at the end of it. We do use prefixes if there is more than one of the groups attached. So here we would focus on the nitrogen, and we see a 2 carbon group. So that is ethylamine. Here we focus in on the nitrogen. We have a methyl to the right and a methyl to the left, which gives us dimethylamine. We focus here on the nitrogen. We have actually an ethyl group, and we have 2 methyl groups. So this is ethyl dimethylamine. Again, alphabetical order regardless of prefix. So that is E before M, basically, is why we went that way with it. So this is the way that you can basically name these guys that have basically groups attached to the nitrogen here. So we'll go with this type of simple naming of simple amines with group, and then just put amine at the end of it. Any questions on that there? All right, so why don't you give the names of these guys and also classify them as primary, secondary, or tertiary here. Okay, let's take a look. So again, we'll go to the nitrogen really. And in this case, we're looking for the group that's attached there. That has 3 carbons, which means it should be a propyl group. And that's pretty much all we need. So this would be a propylamine. And this would then be a primary amine, as it is directly attached to really just that carbon right there. Any questions on that one there? Looking at this nitrogen, it is attached to 1, 2, and 3 carbons. So this would be a tertiary amine. We got our ethyl group to the left. We have a methyl group to the right, and one more methyl group there. So that is a dimethyl situation happening. So we're ready to put it in alphabetical order, E before M. So that's going to give us what we saw on the previous page, I think, ethyl, dimethyl, amine here. Any questions on that? Excuse me. All right, let's talk a little bit about aromatic amines and how we go about naming them. So we do a little different sort of things with these guys. There is that sort of historical amine group there that's on a benzene ring. And that is aniline. So much like we saw with toluene and so forth, that is sort of a historical name. Sometimes people will also call it aminobenzene for the amino group, the nitrogen containing group that's on top as well. So here, if we look at this, that is going to be our aniline as the base of the name. And then we do have a bromine that is 1, 2, 3, and 4 carbons away. So that is our 4-bromol. Now, in this particular case, we could have some groups attached to the nitrogen. So we do a little bit of naming difference. So here is aniline. But we do have a methyl group here, which is that line that's sticking out there with nothing at the end of it. It is not attached to the ring. So typically we use numbers to indicate where on the carbon ring a group is attached. But in this case, it's not really attached to the carbon at all. It's actually attached to the nitrogen. So in these situations, what we do is actually we just use N to represent that it is attached to the nitrogen instead of a number. So that is why this is called N-methyl, because the methyl group is attached to the nitrogen. So that is what the N-methyl stands for. So there is no real numbering of the nitrogen because there's just one. So unlike when something's attached to a carbon where we number the carbons to indicate where it's at, if we do have in an amine a group that's directly attached to the nitrogen, we would do N. Question on that there. Now, what happens if we have this? Nice circle. There we go. And then. So what groups do we have attached there to the nitrogen now? We have a methyl group and we have another methyl group, right? So that's going to be dimethyl. And we can use aniline here if it's attached to the benzene ring, but they're both attached to the end. So when we have a group that's attached to the same carbon, two groups that's attached to the same carbon, we give two numbers usually, right? So here we would actually give two N's. So just like we would do with the numbers, this would be N, comma, N dimethyl aniline to indicate that both of those methyl groups are attached to the nitrogen. So you'll sometimes see that and go, that kind of looks weird with all the N's hanging out there. But in this case, kind of like when we would give two numbers like 2, 3 or 2, 2 dimethyl, we would say NN to indicate that both of those groups are attached to the nitrogen. Any questions on that there? By the way, this amine right here would be a secondary amine, right? It has 2 carbons directly attached to it. This amine that I drew up here would be a tertiary amine. It's attached to a carbon there, and a carbon there, right? So that would be 3 carbons that the nitrogen is attached to in this particular case. Any questions on that there? So that's kind of a weird thing that happens with nitrogen containing groups. Sometimes if the group is attached to nitrogen, like I said, they use kind of the N instead. All right, so why don't you write the common name for each of these guys here? And then why don't you also maybe draw, let's do ethyl propyl amine. All right, let's take a look. So we'll start here with the nitrogen. We have this guy, which is a methyl group. We have this one, which is a ethyl group. And we have this one, which is also an ethyl group. So that's two ethyl groups, which gives us a diethyl happening. So put it in alphabetical order here. We would go with the diethyl first, followed by the methyl, and followed by amine here. So diethyl methyl amine. Any questions on that one there? Coming through here, we have our benzene ring with the nitrogen, which is going to be aniline. Here, attached to the nitrogen group is a ethyl group. So again, here we would want to use N-ethyl aniline here. Again, the N indicating that the ethyl group is not attached to a carbon, but directly attached to the nitrogen. Any question on either of those two? Now, if I want to draw an amine, I know it's a nitrogen containing group, so that is frankly where I'm going to start with. And I'm just going to work one way or the other and give me some groups. So propyl is a 3-carbon group. And ethyl is a 2-carbon group. And I'm just going to put my hydrogens in like normal here. And this guy would get some dots. Now there's one extra thing that's missing. This needs a hydrogen to finish it out. So the nitrogen does need that hydrogen. So remember that if there is one group, carbon group attached, it will have 2 hydrogens. If there's 2 carbon groups attached, it will have 1 hydrogen. And if there are 3 carbon groups, like over here, it will have no hydrogens attached to the nitrogen. So that's an important aspect there. Otherwise, you can think about it, nitrogen will be a little bit short in terms of the octet rule, if you want to remember it that way as well. It would have just a bond to carbons and the non-bonding electrons. Any questions on that one? Okay, here's the line formula for amines. Again, you basically just write in the NH2 at the end there to indicate that it is an amine. And obviously you can do your squigglies here off of the nitrogen for whatever carbons that you need. This would be 1 and 2, so that is ethyl. This would be 1, 2, and 3, which is propyl. So that's ethyl propylamine. Once again here, that is 1 and 2, which is ethyl. That is 1 and 2, which is an ethyl. And then obviously at the end there is just 1 carbon, which would be a methyl. So that's how we get to our diethyl methylamine. And then obviously here, 1 carbon, 2 carbons, and 3 carbons coming that way, which gives us our propyl part of the name and amine at the end because it's a nitrogen containing group. And again, in each of these, there really is some non-bonding electrons on the nitrogen, although a lot of times people will kind of leave them off, but they are there. Any questions on that there? So let's talk a little bit about solubility of amines and hydrogen bonding. Primary and secondary amines with less than 6 carbons are soluble in water because they can hydrogen bond. Remember that to hydrogen bond, you need a bond between hydrogen and nitrogen, oxygen, or fluorine. So if you have a primary amine, you basically have this going on. We'll just steal the line structure. That is a bond between nitrogen and hydrogen there, so that's able to hydrogen bond, which means when it reacts with water, it also is able to hydrogen bond with it between the more negative nitrogen and the more positive hydrogen in water, so that makes it soluble. A secondary amine also has the ability to do the same thing. We'll just steal a guy over here, we can hydrogen bond with it there. Why can a tertiary not hydrogen bond? A tertiary amine looks like this. What is it missing to hydrogen bond here? Kind of missing the hydrogen. Yeah, so it doesn't have the hydrogen on the nitrogen, so it doesn't have the ability to hydrogen bond. So that's why tertiary amines cannot hydrogen bond. cannot actually hydrogen bond with itself, but they can hydrogen bond with water, and it's really going to be able to hydrogen bond only through here. The hydrogen from the water is actually going to be able to bond to the nitrogen, but it cannot hydrogen bond, for example, with itself and water molecules. So that does affect the solubility of it. Primary amines can form more hydrogen bonds than secondary amines, and tertiary amines have no hydrogen on the nitrogen and can only hydrogen bond with water from the nitrogen, which really decreases the solubility of it. If everybody has the ability to kind of hydrogen bond with the hydrogen to the oxygen in the water, it creates a lot more availability of it to be soluble. So like alcohol, smaller amines, including tertiary ones, are soluble because they can form hydrogen bonding. But the tertiary ones cannot hydrogen bond with itself, but can still sort of participate in hydrogen bond if somebody else provides the hydrogen, like water provides the hydrogen in that case. So they are fairly soluble. Amines with less than 6 carbons, the effect of hydrogen bonding is diminished. So again, the same idea, you know, as you build out way too much carbons all around, it just gets in the way of it being able to interact well with water, and the solubility really does start to go down a lot above 6. Pretty much as we've seen pretty much with most organic guys, that kind of 5, 6 number of carbons is like the magical number where solubility kind of drops off, because the molecule gets really too big and it prevents water from really getting in there and interacting well with it. But if you got somebody that has a group that can interact with water and it's got like less than 5 carbons, you know, it probably will be fairly soluble because it does have the ability to hydrogen bond. So which of the following are soluble in water? This one, which is a primary amine, should definitely be soluble in water because it has the hydrogens here to hydrogen bond with water in a couple places. This is a secondary amine, which also still has the hydrogen there, so it should also be soluble in water just because it can hydrogen bond. This is not an amine, this is an alkane, which is all nonpolar, right? Which means it's not going to have any place or way to interact well with water. It's going to try to use dispersion forces. Water is going to use hydrogen bonding. Not so good on that particular one. Any questions on any of those there? Now, amines, as I mentioned, because they are really derivatives of ammonia, which is a base, they pretty much act as a base. So they could kind of do a traditional sort of acid-base reaction, even a Bronsted-Lowry sort of definition where the water will act as the acid and it will donate that H plus over to our amine that's going to act as the base. The result of that is, just like we talked with Bronsted-Lowry, we get an extra H plus on this guy. So if you add an H here, we're up to NH3, and the plus makes it a plus. And when water loses the plus, it is left with hydroxide, basically. So amines, because they're really bases, can pretty much do acid-base reactions. And it is sort of the Bronsted-Lowry definition of that H plus going from the acid to the base, right? Which will accept the H plus in that particular case. Like our conjugate acid-base pairs, which would be these guys and these guys, where the only difference is the 1 H plus on both sides, right? Now, neutralization forms of amine salts. An amine salt is formed as a reaction of this. So this would be sort of like an amine salt here. Amines react as a Bronsted-Lowry base to neutralize things like citric acid. So if you take an amine with an acid, so something like a strong acid, what will happen again is the same Bronsted-Lowry. We're going to donate the H plus over. This guy gains an H plus, gains a positive charge. And if you think about when that H goes away, we are left with Cl minus, which is where this guy comes from, basically. So as that H plus transfers over, that is what we're left with. And it's really the same idea. This part and this part are partners, and I scratched out the H there, but the HCl and the Cl minus are Bronsted-Lowry kind of conjugate acid base pairs. Same thing is going to happen here. Once again, on the bottom here, our H is going to come in there, our H plus. The result of that is we gain one more hydrogen here, and we also gain the plus charge. And once again, the only thing left over is our chloride. So these guys are what are referred to as amine salts. So when you react an amine with an acid, a true acid other than water, you will get basically these salts that's being formed. It's kind of the same idea as when we take an acid plus a base, you get a salt and water, right? And a salt is really an ionic compound, right? A positive, negative guy that's basically formed. So it's the exact same sort of idea that happens with amines. We're not going to worry about properties too much of ammonium salts, but some of them are used obviously in a lot of sort of drugs as well, like Benadryl, Sudafed, are a lot of these amine salts. And it's maybe some illegal sort of drugs as well, like cocaine as well, are amine salts. Alkaloids are the active compounds produced by plants that contain nitrogen. So this is nicotine here. And again, we have our amine group happening there really on both sides as well. Caffeine, also a all the things are good for you, right? Our amines are here as well. It's a stimulant, as you might know, if you drink a lot of it, I suppose. And morphine as well. It's also some of these what are sometimes referred to as alkaloids. So morphine, caffeine, and cocaine there is what are referred to as alkaloids, and they're found in amines and plants. All right. So I want you to draw these two guys here, see what you come up with. Methyl would be 1, and it really doesn't matter which side you sort of draw it on. We're going to put in our hydrogens here to get to 4. Now we also need to remember to put in some hydrogens, so it would be 1 hydrogen. Now you might be asking, how do I know how many hydrogens to put in there? You can remember that these guys are really based off of ammonia, which has 3 hydrogens. Yeah. So one way you could remember it is if it is a primary amine, you would have something like this, maybe. So 1 carbon, 3 minus 1 means I need 2 hydrogens. If you have a secondary amine, it will look something like this. I have basically 2 carbons, so 3 minus 2 means I need 1 hydrogen left. And if you have a tertiary amine, that is 3 carbons. 3 minus 3 is no hydrogen. So you can basically take 3 minus the number of carbon groups that are attached to the nitrogen, and that will tell you how many hydrogens you should lay up there in that particular case. So as we saw here, we had basically 1 and 2 carbon groups attached. So 3 minus 2 is 1 hydrogen should end up there on the nitrogen. Yeah. Any questions on that there? All right, so 2-chloroaniline is a very badly drawn benzene-ish ring with an NH2 group there. By the way, this is attached to 1 carbon, which means 3 minus 1 is 2 hydrogens it should have. In this case, the 2-chloral is attached to the actual carbon because there's a number. If it was attached to the nitrogen, what we would say instead of number? N, right? So since it doesn't say N, it's a number. We know it's attached to the actual carbon group. And we also know that where that NH2 is attached to the ring should be carbon number 1, which means next door there would be carbon number 2, where you would lay up the chlorine in that case. Any questions on that there? Okay. All right, the last sad of the groups that we're going to talk about is the amides, and the amides are kind of like a carboxylic acid, except it's got the nitrogen group attached to it. And that's because it's made up, as we will see, a carboxylic acid and an amine coming together will make an amide. So an amide has that functional group, which is kind of backwards on this picture, but right there. Tylenol is an amide, contains acetaminophen, which is an amide right there. And it has that group that's attached. So amides are really made up of, like I said, pretty much the combination of a carboxylic acid and an amine. So you basically can either put an amine or an ammonia could even be used, but basically when those two guys come together, it's how your amide is made. So if you take a carboxylic acid and you take like an amine here, you might be able to imagine what will come out when we put these together, and it is going to be our good friend here, some water. Yeah, so water is going to come out, kind of like the esterification reaction where you take out water and basically squish both sides together. That's essentially what's going to happen, and you would make your amide, which would look like this. Everything's the same, except obviously I took out water and I squeezed them together, and there is our amide group right there. So the formation of an amide is made by really a carboxylic acid and also either ammonia or an amine in a lot of cases, basically again taking out water to do so. Question on that there. So as we see here, our making of the amide, once again, take water out and basically just squish both sides together. So here goes the water, and then basically just connect these two guys together. The connection, though, when you do put them together, it always has to connect like the functional group looks like this. Yeah, so it's got to always have that connection. Heading to the nitrogen side, it will be the amine. Heading to the carbon oxygen side will be your carboxylic acid side. But that is always where they will connect together. So you don't even have to worry about if you want to think which hydrogen oxygen to take out, just take out water and make that connection. And basically everything on the left-hand side of it, the connection, the right-hand side of the connection stays. You just put it all basically together. And that's what we see here as well. Again, taking those guys out, these two guys get squished basically together. So if we were going to draw this, once again, it may be helpful for you to turn one of these guys around. So if you wanted to, you could turn this amine around like so. And once again, we're just going to take out the water, right? Which means the connection should occur up here, right between those two guys. Everything will remain exactly the same. So this part is exactly the same. My carbon oxygen double bond is exactly the same. I am clearly going to X out everything that's in the box at this point, and that is going to give me my amide connection right there. And there we go. Yeah, so that's what we got going on right there. Obviously, there's water that comes out of it as well. So much like this esterification reaction, you're just going to kind of back those kind of hydrogen to hydrogen, take out the water, and then squish everybody together. But you always, in an amide, got to have, obviously, that connection. That's what makes it, obviously, an amide. So that's how those guys do. That's also how I knew I should go to the top there, and that's where it should connect, because that's where the carbon-oxygen double bond is at, and that will give us the proper connection. Any questions on that there? Go. So naming amides, not interested, not interested, still not interested, not interested. Nah, not interested still. Bless you. So you don't have to worry about naming amides. So urea here is end product there, a protein metabolism, and it is also an amide. You can see the carbon oxygen nitrogen bond there. Some barbiturates as well, or amides. Aspirin substitutes, like we saw earlier, are acetaminophen, also amides as well. We are going to talk about the two reactions of amides. So you do need to know the functional group of an amide. You do need to know how they're made, and you do need to know these two hydrolysis reactions. And they're going to be kind of similar to what we talked about with the hydrolysis reaction. Earlier, we have an acid hydrolysis. So in an acid hydrolysis, you will get back both parts of it. So in this case, both parts of an amide is a carboxylic acid and an amine. So when you do the acid one, much like what we talked about with the carboxylic acid one or the ester one there, you will get both parts back like they normally come. So if we take that one that's on the bottom, let me draw it a little bit bigger up here. So we have this, and we're going to add some water here. And obviously it's going to be an acid catalyzed reaction that's going to take place. So the first thing that we know for sure is just like how we put it together, that is exactly where it's going to break apart. So we might as well just draw our parts that we're going to recreate here. So we will have this part, and we will have basically this part right here. There we go. Now, in this particular case, we are going to, and there is HCl in here as well. Thank you. There you go. So in this particular case, we are going to put back together our carboxylic acid. So we're going to put the OH back. So you can take the OH from here, and that's going to get us back our carboxylic acid. And in this case, we're going to add back in the rest of the stuff. So that is 2 hydrogens. And it will become basically ammonia. It has a plus charge, and that leaves us chloride, which has a minus charge. So in this case, you produce a carboxylic acid, and you do produce an ammonium salt. So you will not get back necessarily, the entire amine in the acid part. You actually get a salt back in this case, because there's an extra acid that's providing H plus in this case. So if we look at another one here, let's do this one here. So if we do this with water and an acid, once again, we're going to break this apart right about there. And we will get, and this is not the one that's on the page, by the way, I just made this one up. Yes. So there's 2, we will get this part. We will also get this part. So once again, we for sure will get the carboxylic acid back. So we just build it out back to give us our OH. And again, if you want to kind of keep track of parts, sometimes it's helpful. That is basically that. Then we have 2 hydrogens that go back to the amine. And because you basically have 2 hydrogens, it's now going to become a positive charge. And then we also have a chloride that's left over. So this is the salt part. Again, a salt and ionic compound, and you get your carboxylic acid back in this particular case. Now, on this one, actually, when you do the salt, so in this particular case, some of these are a little bit bigger to see. We'll go with this one here, I think. So if we borrow this guy here, we're going to break this apart, and we're going to basically do a base hydrolysis. So something like sodium hydroxide plus some heat. And again, we'll get the parts here. So we'll get our part of our carboxylic acid. And we will get our amine part coming off of here. And in this particular case, we are going to get the amine back. So to get the amine back, we really just need a hydrogen to come back. But what's left after we sort of take the hydrogen off of there is really a negatively charged oxygen and a positively charged sodium. So to rebuild our carboxylic acid, we're not going to get the whole carboxylic acid, but to make it look like a carboxylic acid, we do need the connection to be the oxygen part of that first. And then that will actually have a negative charge, and we will get our sodium. So we will make a carboxylic acid salt, kind of like the soap there, and we will get the amine back. So a little bit different than the carboxylic acid one. In the acid hydrolysis, we actually get the carboxylic acid back, and we make a ammonium salt. And in the base hydrolysis, we actually get the amine back and make a carboxylic acid salt. So sort of opposites of each other. Any questions on any of those there? Any questions? No, good. All right, that's the organicness of the day. All right, so we're gonna talk about carbohydrates here in these last few chapters, 13, 15, and 16. Again, whatever is covered in the lecture parts, the recorded lecture for 15 and 16, and the one we're talking about here is what you are responsible for. Again, it may not be everything that's in the chapters, obviously. So here we're going to go back and talk about carbohydrates, all the good Thanksgiving stuff coming up here. We've got some bread, some pasta, that's good stuff. We have hands waving to us. All right. So the first thing we're going to talk about with carbohydrates is what is referred to as a chiral molecule. And a chiral molecule is basically a carbon atom that has 4 different groups attached to it. So a lot of times in carbohydrates, we look for what is referred to as the chiral carbon. And that would be a carbon atom that basically has 4 different groups attached to it. If a compound is chiral, what that means is if you take that compound and put it in front of a mirror, the mirror image that stares back at it, and you take out the mirror image, you cannot superimpose it on the original image. That is why the hands are there. If you take this hand in front of the mirror, you get this hand staring back at you. Yes. If you take this hand out of the mirror, you could take this reflection from the mirror. You can rotate it as much as you like. You will never get them to sit perfect on each other. We could put it down like this. Thumbs are good. Palm up, palm down, not so good. Palm down, thumbs on the wrong side. So you could try to rotate as much as you like. Don't hurt yourself. But you will never be able to get both of those images to sit perfectly on top of each other. And that is what a chiral molecule is. You take the mirror image out of the mirror, and even with as much rotation or movement as you want, you can never get it to fit perfectly right on top of the original structure. And that is, again, what a chiral compound is. In terms of carbohydrates, we oftentimes, like I said, look for a chiral carbon. And the way you can recognize that is that carbon will have 4 different groups attached to it. So here's an example of a chiral compound. This is a carbon in the middle, and this carbon has 1 group, 2 groups, 3 groups, and 4 groups attached to it. So that is 4 different groups that are attached. If you stick that in front of a mirror, this is the reflection that you get. And then the oxygen, the orange on the back. If you pull out that image, you can continue to rotate it as much as you want. Something will always be in the wrong spot. So as you can see there, the bromine and the chlorine overlap, which is not what we're looking for. If you rotate it around, they will never end up being in the right location, and they'll never be able to superimpose on one another. It is hard to visualize. You might think, oh, I'll just rotate it one more time, I'll be there, but it will or will not end up in the right spot. Now, opposite of that, or what are referred to as achiral molecules. Achiral molecules basically have mirror images that if you pull out the mirror image, it will fit perfectly over the original structure. So achiral mirror images do superimpose. Chiral molecules, they do not. So if you have an achiral molecule, it basically means you do not have 4 different groups attached. So here we have 2 bromines, which obviously are not 4 different groups. Because you have that extra similar group, that allows you, when you take out the mirror image and you do some rotation, that you're actually going to be able to get everybody kind of sit on top of each other perfectly, because you actually have 2 of the same group. So there's a better chance that they're going to line up than they're with a chiral molecule. So chiral, the way you find a chiral carbon, 4 different groups attached, mirror image will not superimpose, non-superimposable. And achiral, you do not have 4 different groups attached, where the mirror image will superimpose. Any questions on that there? So here's some pictures of chiral and achiral. We have our chiral hands here. We have our chiral golf club, achiral soccer ball. You take the reflection of that, it's basically kind of the same. Our right-handed scissors, as opposed to our left-handed scissors. I'm not going to get into that. This is our achiral cup here, and our shoes would be chiral. Obviously, same idea. You'll be opposites of each other in the mirror image. All right, so we want to identify, are these chiral or achiral? So take a moment and identify. Okay, let's take a look. So here we can focus really on the carbon, and we have a chlorine, which is different than a methyl, that's different than an ethyl, and that is different than a hydrogen. So that is 4 different groups attached. So that would be a chiral compound. That means that its mirror image will not superimpose on it. We look at the carbon here, we got a chlorine that's different than a methyl, that's different than a hydrogen. Uh-oh, that is the same. So that is not 4 different groups that are attached. So that would be achiral. And again, the mirror image on this guy will superimpose because it's achiral. And lastly, here we have a chlorine that's different than a methyl, that's different than a bromine, that's different than a hydrogen. So that is 4 different groups, which means it will be chiral. And again, here the mirror image will not superimpose on each other. Any questions on any of those there? Hope it agrees. I think it does, so that's good. All right. So let's talk a little bit about Fisher projections. Sometimes we can represent 2-dimensional drawings in sort of a 3D sort of picture. We oftentimes will always place the more oxidized group on top. If you see vertical lines in place of dashes for bonds that go in the back. So any type of dash one means it's sort of going behind the paper, if you will. Horizontal lines are wedges, mean that they're coming forward. So sometimes you'll see things drawn with like a dash line, which means it's again kind of going behind the paper. You'll see like a wedge sort of drawn. It means it's sort of coming out of the paper. And sometimes that's how they'll kind of show 3-dimensional drawings on just a 2-dimensional sort of paper. And again, these dotted lines would sort of mean the same thing here. The most oxidized group that we will see with sort of carbohydrates are these type of guys here, either like our aldehyde group or our ketone type group will be found towards the top of the molecule. Another very common way that we see carbohydrates drawn is frankly just like this, kind of like line structure, where everywhere they kind of cross is a carbon. So that's another way that I will see. So even though there's nothing written here, there is a carbon there. And by the way, that is a chiral carbon, as it does have one group here that's different than this group, that's different than this entire group, and that's different than this entire group. So that would be the chiral carbon. That's right there in the middle. And again, sometimes in carbohydrates, it's kind of like line structure. It just kind of draws some lines, but there are the carbons kind of where they intersect is typically where you find the carbons. in these sort of carbohydrate structures. Now, we also will sometimes talk about either D or L versions of molecules. L for the most part means left, and D for the most part means right. I know, why did they use R? It's for the reason, but D means right and L means left. And what we're talking about is the determination of that is the very last chiral carbon furthest away from the most oxidized group on top, which side the OH group is on. So if the OH group is on the left-hand side, it would be the L. If it's on the right-hand side, it would be the D, and that would be the furthest chiral carbon from this group. So in this case, this guy right here would be the chiral carbon. Why is this group right here not the chiral carbon? What's attached to that carbon? 2 hydrogens, right? And an OH. So 2 hydrogens is the same. I will say 100% of the time, but pretty close. You could usually find the very last chiral carbon like right above that guy. So it won't be some odd percent of the time. Right above that CH2OH in carbohydrates is probably your last chiral carbon. And if we look at it here, the last chiral carbon's here because it has one group here that's different than this group, different than the OH, and different than that. And we see the OH there on the left-hand side. So that would be our L, a glyceraldehyde here. Same thing here. This is our last chiral carbon, once again, right above that group. And here we do see the OH on the right-hand side. So that would be the denotation of this sort of carbohydrate group here. All right, so indicate whether each pair is a mirror image that cannot be superimposed. That's like a double negative, I think. So the guy on the left and the guy on the right, they are mirror images of each other. So determine if they cannot be superimposed. Okay, so what we really know here is there's a mirror right there, and on the right here, it's our reflection of what's on the left. But what we do know is a chiral molecule cannot superimpose, right? And an achiral, you can superimpose. So really what we want to figure out is, are these chiral or achiral? So if we look at this guy, is this compound chiral or achiral? This compound is chiral. That's one group that's different than this group, that's different than this group, that's different than this group, which means this is a chiral compound, which means it cannot be superimposed. But to answer the question, because it's a double negative, yes, the answer is yes on this one. This is one that cannot be superimposed. So no superimposing happening here. How about the guy on the bottom? It is a chiral or achiral. It is achiral because we got two groups here that are the same. That means that the mirror image here can superimpose. But to answer your question, the answer would be no for the question because it cannot be superimposed. It's a double negative, cannot not be superimposed. So I didn't write the question. I don't know, but so I'm going to just say yes, it could be superimposed. Yes, it can be superimposed. But if I go back and look at the answers to the questions, the reason why one says yes and one says no is because it's a double negative. So the yes really means no, and the no really means yes on the question. I don't know. It happens sometimes. All right. You see, because you're going to ask me that says yes and no, right? And then it's like opposite what I just said. I don't know. So double negative, just like turn it around. All right, let's talk about carbohydrates officially. Carbohydrates are really composed of carbons, hydrogens, and oxygens. They are also sometimes called saccharides or sugars, and all the good stuff there, right? In the picture. So carbohydrates are produced through photosynthesis of plants, such as glucose. gets synthesized from the CO2 in the water in a nice little cycle through respiration. So we got carbohydrates and oxygen making some water and CO2 with some energy and kind of going in a nice little circle. There are some different types of carbohydrates, and we're going to talk about each of these in a little bit more detail as we go through this chapter. But the simplest carbohydrates are what are known as monosaccharides. They're basically one guy by themselves. Disaccharides is basically when you take two monosaccharides and basically put them together. And surprisingly enough, when you take one carbohydrate and put it together with another, out goes water, basically. So you basically take water out and stick them together is how you make a disaccharide. Polysaccharides is just a really long chain of carbohydrates attached to carbohydrates attached to carbohydrates, where you basically just take out water in each of the cases and keep sticking all the carbohydrates on in a long chain. That's what we see here. They could actually go through hydrolysis, except for monosaccharides, because those are the base units. A disaccharide, you add water, which is hydrolysis, and it breaks it back apart. So when you take water out, it puts it together. And if you put water back in, you could break apart a bigger sugar into a smaller sugar through a hydrolysis reaction. And if you have a polysaccharide, which contains a lot of sort of sugar units, you can put a lot of waters in there and break them all apart. So let's talk a little bit about some monosaccharides and what they consist of. Monosaccharides will consist typically of 3 to 6 carbons, and they will have really an organic group on the top. So they'll either have an aldehyde group, which hopefully we still remember is this group, or they will have a ketone group, which is that 3-carbon run group at the top of it as well. So most monosaccharides will have one of those two kind of groups at the end of it. And it also tells you what type of monosaccharide, depending on which group is there, either the aldehyde group or the ketone group. Those are the most oxidized groups, which means they should be at the top of the carbohydrate. They also will have a number of OH groups, hydroxyl groups. So these are OH groups attached as well. That's also why sugars are pretty soluble in water, because they have a lot of OH groups. So they're able to interact well with water and do hydrogen bonding. Now, if it does have our aldehyde group on top, this is what is referred to as an aldose, because it's an aldehyde group. So it's referred to as an aldose. We also could classify this carbohydrate based on the number of carbons, as 1 carbon, 2 carbons, 3 carbons, 4 carbons. 4 carbons is what is referred to as a tetrose, like tetras 4. Penta be 5 carbons, hexa is 6, those would be 6 carbons, and triose would be 3 carbons. So this would be an aldotetrose. Aldo because it has the aldehyde group on top, tetrose because it has 4 carbons. And out of those 4 carbons, how many of them are chiral? Is this a chiral carbon? It is not, because it needs 4 different groups. It only has like 3 attached. Is this a chiral carbon? The answer is yes, because it has this whole entire group, which is 1 group, which is different than this group, which is different than this group, and it is different than this group. So that is 4 different groups. So that actually is a chiral carbon. Now, what about the carbon underneath it? Is it chiral? So is this carbon chiral? The answer is yes. And that was a 50-50 shot, so that's good. And that's because now this entire thing is a group above it, right? Which is different than this guy, which is different than this guy, which is different than this guy. So that is 4 different groups attached. And the carbon at the very end there is not chiral, right? Because it has the 2 hydrogens. So once again, this particular guy actually has 2 chiral carbons, this guy and this guy, which means if I know, is this D or L, which one would it be? It would be D, as this is the last chiral carbon furthest away from this group, and the OH is on the right. So this would be the D form of this guy. Any questions on that? All right, we're gonna lay it up here and talk about a few things before everybody runs out.